here at Everactive. It's my pleasure today to introduce one of the co-founders and current co-CTOs of Everactive, David Wenzloff. Dr. David Wenzloff is also a professor of electrical engineering and computer science at the University of Michigan. So Dave, take it away for our special Earth Day webinar.
All right, thanks, Brian. And let me start off by wishing everyone a happy Earth Day. Thank you for participating in this webinar today. So today we're going to be talking about self-powered sensors for a sustainable future. And here's an agenda of or an overview of my talk. So we're going to start by talking about the environmental impact of the IoT. Then we'll transition into why batteries are standing in the way of realizing a pervasive vision of the IoT. And then we'll introduce some self-powered solutions to that battery problem. So I wanted to start with a couple stats on the annual US energy use and emissions shown here on this slide. And so on the left, we're showing total US energy consumption by sector, and on the right, US CO2 emissions or greenhouse gas emissions. These numbers are from 2018, because that's the most recent data available from the DOE and the EPA. And just starting with energy consumption in the US, the total energy consumed in 2018 is 101 quadrillion BTUs, or British thermal units. And I just wanted to maybe put that number in perspective for a second, because a quadrillion kind of sounds like maybe a made up number. So first off, what is a quadrillion? A quadrillion is 1,000 trillion BTUs, or you can think of that also as 1,000,000 billion BTUs. And just to put that number in perspective, one 20-gallon tank of gas in your car stores 2.5 million BTUs of energy. So 101 quadrillion BTUs is equates to about 40 billion tanks of gas, which is an enormous number. There's 7 billion people on the planet, so about 3 tanks of gas per person. That's the amount of energy we used in the US in 2018. This pie chart breaks down where that energy goes. And you can see most of that goes into producing electricity. The second largest consumer of energy is in transportation. And then the third largest is industrial at about 1/4 of the total US energy consumption. And then residential and commercial make up the remaining part. But notice that's a much smaller fraction compared to those big three. If we then focus on CO2 emissions, again, the total CO2 emissions in the US in 2018 was 6,600 million metric tons. And just to put that number in perspective as well, your average passenger car consumes about 4.6 metric tons of CO2 per year. And so 6,600 million metric tons of CO2 equates to about 1.5 billion cars, car emissions. Again, CO2 emissions per year in the US. And if we look at those same sectors, if we break that down by sector for emissions, you see the big three: transportation, power generation, and industrial are the largest. Here, commercial and residential are grouped together. And then the fifth bar is actually agriculture, and that rounds out the top 5 sources of greenhouse gases in the US. But the thing to point out here is industrial is about 1/4 of the total CO2 emissions in the US as well. So if we look at the environmental impact of the IoT, or how IoT has impacted the environment today, I wanted to pick on a few examples that I think a lot of us are probably familiar with for starters, and then we'll dig into some others that maybe we're not as familiar with. And the first one is smart homes. I think many of us are familiar with Nest sensors, Honeywell, Emerson, all coming out with smart thermostats. And smart thermostats have been shown to be able to save on average of 30 to 40% of the energy consumption in an average household, which, you know, if all of us were to adopt that, that's a pretty significant savings. Similarly, commercial buildings in cities that have adopted smart building technology can show a potential savings of on the order of 8 to 20%, kind of depending on what that building's utilization is. And then finally, just talking about pollution in cities, the WHO estimates 4.6 million deaths each year due to air pollution related causes, which when I heard that number, that's just a staggering number for me to think about. And there have been IoT solutions to help address this problem, for example, by putting air quality sensors, distributing those across the city, and then using that, for example, in Korea, to do pollution-based transit routing, which I think is a pretty interesting application. But beyond that, just gives you better visibility on what's going on in terms of pollution in cities. If we focus our attention then on the industrial IoT, and remember, the industrial sector consumes about 1/4 of the US energy and produces about 1/4 of the US greenhouse gases. If we just focus on industrial applications and where the IoT has helped out, I'll start on the left with steam systems. So in particular, steam traps, which are condensate release valves in steam systems that are a common point of failure and also a large contribution to energy lost or waste energy in steam systems. Steam, by the way, just a quick side note, is still a widely used method for transferring energy in industrial applications. You know, it's been around for over 100 years and it's still widely used today. It turns out it's a very efficient way to transfer energy. And every steam system has steam traps, and we estimate there's around 65 million steam traps worldwide, but that's a pretty difficult number to estimate. And on average, these fail every 3 to 5 years. And if you do the math there, that's a significant amount of waste steam that just essentially gets recirculated into the condensate line, wasting energy if you're using natural gas to produce that steam, wasting water, and producing excess CO2. So shifting our attention to rotating equipment, I think a pretty interesting stat here is that worldwide, industrial electric machines use about 53% of the world's electricity. So think about that for a second. You know, if we could monitor the condition of all of those industrial electric motors and identify ones that are not running at peak efficiency, and let's say just improve the efficiency by 1 or 2% on each one of those machines, we could have a significant impact on the complete world's electricity utilization. So just because, you know, these applications are so widespread, even small savings can have dramatic impacts. And then lastly, on tanks and piping, on average, about 3 million gallons of oil are spilled each year. And the IoT has been applied to this problem by monitoring the thickness of, for example, the walls of pipes or looking for corrosion, and identifying or predicting if there's going to be a leak in either of those, where someone could go do some preventative maintenance there and prevent one of these spills. Okay, so those are some spot applications of where the IoT has been applied to sustainability, but really we won't realize the greatest impact of the IoT on the environment until we have pervasive monitoring. So really think about this as you know, a world where we have real-time visibility across all assets, and what that allows us to do is not just focus on individual applications and improving the efficiencies of those, for example, steam systems or rotating machinery, but be able to be able to aggregate all of that information at, let's say, a facility level or a regional level, in order to make better decisions on how to operate those facilities. So again, really that comes from pervasive monitoring. So monitoring all assets, not just a fraction of them. So that begs the question, how do we get to a world where we have pervasive sensing? And at Everactive, we firmly believe that batteries aren't the solution, that batteries won't get us there. And I'll use this plot really to talk to that point. So if we think of an IoT device as really the next generation of computing platform, where other compute platforms included desktop machines, laptops, mobile devices, and wearables, for example. If we think of IoT devices as the next generation of compute platforms, you know, really to get to a world where you have one device per thing, we're talking about a world with potentially, for example, 1 trillion IoT devices out there monitoring these. And today, you know, we operate on the order of about 10 devices per person. If you kind of add up all the devices around you and maybe, you know, how many batteries you're in charge of replacing or recharging when they die, it's about 10 per person, you know, so maybe 20, 30 per household. You can kind of think of it like that. And that's a more manageable number, let's say. So it's more manageable to operate those devices from batteries and replace or recharge them when they need it. But when you think about 1 trillion batteries, I've got a statistic on the right side of this slide. If each one of those 1 trillion devices had a 3-year lifetime, we would still be changing 1 billion batteries per day. And with 7 billion people across the planet, that means every man, woman, and child is replacing a battery once a week across the entire globe. And that's assuming each one of those IoT devices has a 3-year battery lifetime. And how many devices do you own today have a 3-year battery lifetime? Probably not too many of them. So really, this is the scaling problem, I think, that our entire electronics industry faces. And analysts' projections have reflected this reality as well. So back in 2012, analysts were projecting that we would hit 1 trillion IoT devices by the year 2015. And you know, we're well beyond that now, and we're far short of that 1 trillion number. In 2017, that was revised to 50 billion devices by 2020. And then in 2018, that was revised again to 25 billion by 2025. So those projections have consistently been revised down and further out in time. And again, I firmly believe this is because of this battery problem that everyone faces when deploying these devices. So shifting gears a little bit, you know, another downside to deploying 1 trillion devices that all operate on batteries is that, you know, that would mean that there's 1 trillion devices, 1 trillion batteries out there that we're now dealing with and potentially disposing of. And you know, just to add some more statistics around that. So, for example, in a mining town in Chile, the percent of water that is used for mining lithium in support of lithium-ion battery production is around 65%. And you know, a number like that really just doesn't scale if you think about scaling the number of batteries you're going to be producing by, let's say, 100 to 1,000x. Likewise, if we continue on our current projections, we'll be disposing of 11 million tons of unrecycled lithium by the year 2025. And if I go back to my 3-year lifetime assumption for 1 trillion IoT devices, we're replacing about 333 billion batteries per year. So really, this beyond just you know, deploying these devices and maintaining the batteries, there's an environmental impact of actually producing and then disposing of all those batteries as well. So, you know, one question is, well, could we rely on battery improvements to basically get us out of this jam? And here I'm showing a plot of the battery energy density and how it has scaled over the last 100 years. So from 1900s to 2010. And you know, the takeaway from this graph is what we roughly see is about a 7% year-on-year improvement in battery energy density. Energy density meaning how much energy I can store in a given volume for a battery. Like how much energy can I put in a AA battery form factor? So that's improved by about 7% year on year. And there have been step function improvements when we introduce a new battery technology, but those steps are not several orders of magnitude. Those steps are you know, more like single digit or two-digit percentage improvements. So if you contrast that to how the semiconductor industry has scaled over the last 30 years or 40 years now, Moore's law scaling has shown a 50% year-on-year improvement for multiple decades. So a dramatically higher rate of improvement in the electronics than what we've observed in battery technology. Okay, so this begs the question, can we operate our IoT device without a battery? Can we run it from a renewable energy source or from harvested energy? So I'm going to call this renewable energy sources at the micro scale, meaning, you know, rather than solar panels on your roof, you know, think 1 by 1 centimeter solar panel or solar cells on a postage stamp form factor IoT device. So, you know, begs the question, is it possible to operate these devices from harvested energy? And so for that, we have to look at the supply and demand of power in an IoT device and from a energy harvesting source. So first, let's talk about on the demand side. So how much power does a device consume, and what is the resulting lifetime if I were to power that device from a battery? So the plot on the left shows power on the y-axis and time on the x-axis for an electronic device, an IoT device that I'm powering from a AA battery or a coin cell, like a small coin cell, like what you might find in your key fob in your car. And you can see, in order to get to a 1 year or even 10-year lifetime on those batteries, we need to be operating in the power range of 10 microwatts to 100 microwatts average power. And again, that's to achieve let's say 3 to 10 year lifetime at those power levels. But that also means after 3 to 10 years, you're changing the battery. You're disposing of the device or changing that battery somehow. Okay, so let's look at what you can do with microscale energy harvesters. So the table on the right compares a few different energy harvesters and how much power you can expect from each of them. So starting with outdoor light, which is really, there's an abundance of energy from an IoT device perspective. We estimate, you know, for a square centimeter photovoltaic cell, you can assume about a milliwatt of power. So, you know, on my graph on the left, that's about the midpoint. The 1 milliwatts, about the middle of the graph. But harvesting from other sources, such as human motion, like heel strikes, for example, in smart shoes, or vibration, like on rotating machinery, or thermal, like heat gradient, temperature gradients, or harvesting from heat. And then finally, indoor light. You can see rough numbers. You know, you assume about a few hundred to maybe down to a couple tens of microwatts per centimeter square is about how much power you can harvest from those sources. So putting those things together, I've drawn this harvested power floor around 10 microwatts, where if you could develop an IoT device that has an average power of 10 microwatts or less, you've got a good shot at operating that device continuously from these small amounts of harvested power from these micro scale sources. Okay, so then how does Everactive enable pervasive remote monitoring? Well, it starts with really our batteryless technology. So we develop our own custom circuits We design them in-house, and we leverage ultra-low power circuit design expertise that we've developed over the last dozen years or so to design wireless or circuits that include radios, processing, sensor interfaces, memory, really all the components of an IoT device, but can operate under that 10 microwatt, I'll call it 10 microwatt floor in quotes. So it really starts with that core chip technology. And then from there, we build full stack solutions. We integrate those chips into self-powered nodes or self-powered devices. Those are the plastic devices we can stick on an asset and power it from heat, for example. We connect those with an always-on network that we deploy in a customer's environment, and then that backhauls to the cloud where we can perform additional analytics and derive insights. To date, we've taken that full stack system and targeted specific solutions in the industrial space. And we've really gone after ones that have maximum impact on the amount of waste energy in those industrial facilities, which in turn maximizes impact on the environment in a good way. So just to dig in a little deeper to that full stack solution, again, starts with, on the left, starts with our custom designed chips, which includes an always-on ultra-low power receiver, includes ultra-low power digital processing, so we can do local compute of sensed data on the node, and also includes energy harvesting power management, so we can interface our chip directly to energy harvesters and operate those circuits continuously from harvested power, which is another key differentiation between your typical battery-powered device, which quite often does not operate continuously. It operates on what's called a duty cycle, or operates intermittently. And the reason it would operate intermittently is to try and save power and extend lifetime. In contrast, if you can get the active power low enough so that you can run it from harvested power sources, you can just operate continuously. You don't have to be intermittent. So we've developed our own network that then takes advantage of those ultra-low power receivers that are on listening all the time to develop an always-on network that enables scalability to 1,000 nodes per gateway with millisecond latency down to any one node, or even groups or subnets of nodes. Then on top of that, we develop our self-powered nodes. We call them Eversensors. These are powered by our custom chips. They include energy harvesters. They're designed to operate from harvested energy alone. There's no battery inside. So they have exceptionally long lifetimes, multiple decades, and can do all of the continuous sensing, computing at the edge, and then communicate through our wireless network back to the cloud. And then on the right at the top level, this is really our interface to our customers. Includes cloud analytics and a dashboard that allows you to gain visibility into what's going on, but also through our insights as a service model allows us to deliver let's say alerts or interrupts, if you will, to our customers to alert them when there is an asset that we have identified as failed or needs maintenance, and they can go address that. So what does that mean for our customers? Out of the box service, meaning you install a device on your asset, it immediately powers up and starts talking to the cloud. No additional maintenance. There's no batteries to recharge or replace, and lifetimes of multiple decades of our devices. And then ultimately reduced energy consumption and reduced emissions, saving money. So next I wanted to dig in on our first two products, just to give you, maybe ground a little bit what I've been talking about in some actual devices that we're building and selling today. And the first one is our steam trap monitor. So this first product is commercially available today. I mentioned before, steam is used in a wide range of applications. It's still widely used today. And steam traps are these condensate valves that are really a cross-industry pain point. They're a common point of failure for steam systems, kind of by design for safety reasons, and contribute to a lot of waste when they do fail, both in water and CO2 emissions. And our first product includes monitors for determining the state of the trap, powers from the heat of the steam, and then streams that information to the cloud. On the right, just showing some projected returns for, in this case, a facility that has 1,000 traps in it. A typical facility could run between a few hundred traps to several thousand traps in one facility. These numbers assume 1,000 traps. And I'll just call out the annual CO2 savings of 28,000 metric tons by monitoring steam traps for failures and then correcting them once they fail. And again, that's on the order of around 6,000 vehicles, the equivalent of the emissions from 6,000 vehicles that were effectively taken off the road. Our second product is a machine health monitor, which is powered by the heat of the motor and monitors electromagnetic fields, vibration, really can look at the efficiency and operational state of motors and stream that to the cloud as well, and enable us to make predictions on the efficiency of the motor, identify when motor efficiency is being impacted by, let's say, the need for lubrication, for example, is a common maintenance item for machines, or in the long term, predicting failure. So ideally, with a continuously monitored motor, we can reduce the electricity consumption of motors. And remember, 53% of the world's electricity goes to industrial rotating machinery, as well as extending motor lifetime, which means fewer replacements and less cost there. Okay, so kind of summarizing the returns for these two products. On the left, for our steam trap monitor, again, this product's commercially available today. At the end of 2019, we had 1,251 traps that we were monitoring, and if you project that number over the entire year, the impact of that monitoring, it equates to 34,000 metric tons of CO2 saved, or 7,000 cars taken off the road, and 59 million gallons of water saved. So significant savings there realized just by monitoring those traps. Our machine health monitor is, we're currently prototyping, we'll be releasing later this summer, the initial production release of that. But just again, showing some numbers there, assuming a 2% improvement in motor efficiency by adopting a continuously monitoring solution like this, you can see the matrix of, in this case, dollars saved. But for the case of 10,000 motors, which is not unrealistic for a single facility, and 200 horsepower motors, that equates to roughly 16,000 homes' electricity usage for a year of savings, just by, again, improving efficiency by, a mere 2%, just because essentially the scale is so high. Okay, so just wrapping up, I wanted to talk a bit about our next generation developments at Everactive and really where we think this can go from here. And I've broken this down into basically two categories, and I'll talk about those separately. So on the left, we are steadily improving the performance of our custom circuits that are powering these devices, and targeting what we're calling an Everactive mode at a power consumption of 1 microwatt. So on continuously communicating with, again, a power of 1 microwatt, well below that 10 microwatt power floor I was showing earlier, what that does is allows you to develop devices that are smaller form factor, use smaller harvesters, or can harvest from much less, let's say, dimmer indoor light or lower temperature gradients, for example. Our next generation device, we're designing to be roughly a form factor of like a double stuffed Oreo cookie. And within 3 years, we've got line of sight on enabling devices that are postage stamp size, both in size and thickness and form factor. You pull all this together, and you have smaller volume and longer lasting sensors. Really means less electronic waste, which is another, I think, concern. With, again, deploying 1 trillion devices, you don't want necessarily all of those devices to be large and producing a bunch of plastic and other electronic waste. And then on the right side, we're also looking at improving the amount of compute we do at the edge, so that we can uncover new insights on the device itself, rather than shipping that data to the cloud, and improving our wireless communication range. All of this intelligence at the edge results in a smaller cloud footprint, which means less processing in the cloud and less data storage in the cloud. So reducing the footprint there by pushing all of that out to the edge where we operate those devices from harvested power. And all of this together leads to a more sustainable future. All right, so with that, I want to thank you again for your attention. I've included our contact, myself and Brian's contact information here. Feel free to, if you have any questions, we have time for questions now. If you do have questions, please use the Q&A feature in Zoom. Type your questions in there. And I see some people have also put them in on the chat. And so I'll hand it back over to Brian to moderate the Q&A session. But thank you for your attention.
Thanks, Dave. We've got a lot of questions here, so let's see what we can get through here. First question is, what kind of data rates can you support with a kilometer range? Is this different for downlink versus uplink? What sort of reliability can you support?
Yes, so the different for downlink and uplink is true. The data rates we are supporting today are for our ultra low power receiver on the order of a few kilobits per second. We primarily use that receiver to offload networking traffic. So we don't use that for primary data communication. We have a separate, we call it a communication radio, that handles the bidirectional data communication to do things like over-the-air updates of the software on our nodes and to send data to the cloud. Our comm radio operates at 200 kilobits per second. And then again, our ultra low power receiver is around a few kilobits per second.
Okay, thanks, Dave. Next question, this actually combines a few different questions. How close do ever-active devices need to be to a hub? And what is the network topology? Is it a mesh network, hub and spoke, et cetera?
Yeah, yeah, good question. So our first product uses our first generation silicon, and the range that we have observed in our deployments, I mentioned we have, the end of 2019, we had roughly 1,200 devices. We've got many more than that now deployed. The rough range we see is around 30 meters to a gateway, and that is in a dense industrial deployment. So line of sight's more like 100 meters. We do not use mesh networking. We use a star network to talk directly to the gateway, and that has advantages in terms of scalability, ease of deployment, enables mobility, and reduces latency of the devices. So there's lots of advantages to being able to talk directly to the gateway rather than having to multi-hop with a mesh network. So we've adopted the star network topology. I want to mention, though, our second gen product, our machine health monitor, is built on our second generation platform. which again, we're prototyping today. The range that we're observing with those deployments, again, in dense industrial environments is around 250 meters. So from a gateway, we can support up to 1,000 devices for a single gateway with a radius of 250 meters in a practical industrial environment.
Thanks, Dave. Moving on here, next question. What's the lifetime of an ever-active sensor before you have to throw it away?
Forever. It's a forever sensor. It's kind of tongue-in-cheek. You know, the lifetime, so there's no battery. There's no battery to wear out. We do local energy storage on the device, but we do that in a capacitor, and capacitors have much longer lifetimes than batteries. We have performed extended lifetime tests on our first generation device, and the lifetime from those tests that we've been told is greater than 20 years, limited by the testing that we did, not because the device failed. So, you know, we're trying to build forever sensors, and we anticipate decades of lifetime.
Perfect. Thanks, Dave. Moving on. For energy harvesting, what happens if the source goes out, if the lights go out, for example, and there's no harvesting available?
Yeah. Yeah, good question. We have been thinking about low power circuits and batteryless operation for, I mentioned we've been doing research in this space for about a decade now, or a dozen years. So we've been thinking about that exact problem for a long time. And, you know, the way to think about that is, you know, you basically, there's three components to how energy is generated or stored or used. And really it's kind of in that order. You have an energy harvester, which produces power. We have energy storage, which is done in capacitors, not batteries. So we can store energy locally in the device. And then you have energy consumption or power consumption, which is the electronics like the sensing, the processing, and the wireless communication. And, you know, there's kind of a you know, multiple trade-offs that you can make when designing a full solution, which include things like volume, size of the harvester, you know, perhaps what you're sensing and what you're processing on the device itself. But you know, we have tuned those solutions for these first two products that I mentioned. For the steam trap monitor, just to give you some real numbers, for example, for the steam trap monitor, the steam shuts off and all heat goes away. Our monitor will stay active for about a day and a half after steam goes away, and that's really plenty of time to see the, you know, the whole steam system cool down and then sit there cold at room temp. Once steam comes back, it immediately cold starts, fires back up, and starts talking to the cloud. Our machine health monitor, we're engineering that to be more like a few days to a week. Once the motor shuts off, heat goes away, device can stay alive for a matter of days. But that is something we can engineer in the final solution.
All right, thanks, Dave. We have time for one more question. Looks like we'll end with this one. How does Everactive compare to the other quote unquote low power IoT offerings on the market?
Well, first of all, we're batteryless. Second, we offer a full stack solution. So rather than just you know, delivering a single chip, a low power chip, or even a low power sensor, or a low power or I should say a cloud platform, we've integrated all of that together to deliver a full solution for our industrial customers. That's a key differentiator. And then on the, we've been talking a bit about the wireless connectivity. I'd say on the wireless side, you know, enabled by our ultra low power receiver, we have the ability to scale to 1,000 nodes per gateway with millisecond latency to each node with a very simple deployment. or pairing and provisioning process. So, you know, from a ease of installation, essentially zero maintenance after that, and then full product or full solution for our customers. I think that kind of all that together differentiates us from other IoT solutions today.
Thanks, Dave. I'll turn it over to you for any closing remarks, but we're at time for questions.
All right.
Anything else to add, Dave?
Yeah, sure. Well, I'll thank you again for your attention today and attending. And you've got our contact information on this slide, so feel free to reach out if you want to discuss any of this further. And happy Earth Day.
All right. Thank you.